morning, good evening, everyone. Welcome to our Tech Talk today. Today's webinar is part of the Tech Talk X series by Digital at INSEAD, dedicated to exploring new technologies, their applications, as well as their impact on management, business, and society. For more information, please visit the Digital at INSEAD website, and a big thank you to our sponsor, Accenture. Our speaker today is Professor Miguel Lobo. He is the Associate Professor of Decision Sciences at INSEAD. He's completed his PhD from Stanford University in computational mathematics. Before going back to academia, Professor Lobo worked on 2 startups in Silicon Valley. As for me, I am Savita. I will be moderating the Q&A today. I am the co-president of the AGI Club at INSEAD. So before we dive in, a quick note on webinar etiquette. The audience will be muted and the video and chat functions will be disabled. Should you have any questions for our speaker, please use the Q&A tab and I will help with moderating at the end. Please ensure the questions are short and to the point. And to help us identify the most relevant questions, you can upvote the questions that already exist. This webinar is being recorded and will be uploaded on YouTube shortly. Thank you, and I will hand over the floor to Miguel.
Thank you so much, Savita. Let me share my screen and get started. Right, excellent. So welcome everyone. Welcome to the seminar. Let's spend the next 1 hour talking about some topics at the intersection between on one side computation and what's going on with machine learning and artificial intelligence, and on the other human judgment and behavior and cognition. My career has been sort of at the intersection of the two, so this is a very, of course, a topic that's very close to my heart. So let me start with the following question for you. So this is currently the world's fastest supercomputer. Came online last year. The HPE Cray Frontier cost $600 million, an amazing machine. It has 9,000 CPUs, 38,000 graphic processing units, which is where most of the computing power is these days in the machines we use. It has the capacity to do over 1 exaflop. That's 10 to the 18. That's 1 with 18 zeros. That's the number of operations it can do in a second. Incredible machine. Consumes an enormous amount of power, it uses an enormous amount of space. Now, if you go back in time, what did these machines look like? These are the holders of the crown previously. So the previous one was Fugaku in Japan. And then before that, there was an IBM machine. Before that, the Sunway Tahoe Light in China. You can see they look very similar. So huge machines fill up an entire warehouse, extremely expensive, consume an enormous amount of power. If we go back about 50 years, what did these machines look like? Very similar. This is the Cray one, a very famous machine when Seymour Cray left CDC to start his own company, a really important machine in the history of computation. Doesn't look all that different. It was very expensive, I think about $30 million in today's money. Also consumed an enormous amount of power with liquid cooling, incredibly clever engineering. We cannot go back another 50 years because we didn't have computers back then. Arguably, the furthest back you can go is to the Colossus, the machine at Bletchley Park that was used to break the encryption codes during the war. Here's my question for you. So buy yourself a cheap laptop, buy yourself a cheap gaming laptop. I could find this for under $700. A Lenovo gaming computer with, it has a decent graphics card, the GeForce 3050. If you go back in time, do you think that the cheap laptop of today would be, say, well, the Colossus? Well, of course, your laptop is much faster than the Colossus. But do you think that your laptop, the machine you might be watching this webinar on right now, do you think it is more powerful than the Cray one, famous Seymour Cray's first supercomputer? And most people guess yes, and then the question is, at what point in time, if you had a time machine and you could go back in time with your laptop, how far back would you have to go for your laptop to have the same computational capabilities as the world's fastest supercomputer? And when I do this with groups, people typically guess around the 1980s, some people say 1990s. You know, I've had actually, at one point, I had a session where I was on stage with Michael Hayden, the former head of the National Security Agency, and he also guessed in the 80s. So that's what most people guess. The answer is just 20 years ago. All you need is to go back 20 years. And a cheap laptop of today, at that point in time, would have been the world's fastest supercomputer. At least, of course, in flops. There's more to computational capabilities than that, but at least in flops. So it's really remarkable. If you look at the computational unit that goes into the Teslas, this was developed in-house. These processors that were developed in-house, the whole system was developed in-house. It has 2 different processors for redundancy. Each of them has 2 cores for redundancy. This thing was rolled out in 21. It goes into every car that comes out of the production line. In 2007, this computational unit that goes into every Tesla coming out of the factory would have been the world's fastest supercomputer. So that's just 14 years from a machine that costs hundreds of millions of dollars, fills up an entire warehouse, consumes an enormous amount of energy. Just 14 years later, it's a chip going into a car, going into every single car rolling out of the factory. So pretty mind-blowing, the progress. So this is the biggest chip you can buy right now by a company called Cerebras Systems in California, about 20 by 20 centimeters, optimized for neural computation, as you might expect. Here's a different kind of computer, and we all have one of these, the human brain. How does it compare? How can we compare? How can we even compare digital computer, which is electronic, digital, against the brain, which is partly digital, partly analog. It's electrochemical processes, very difficult to compare. But there's a couple of ways we can compare. One is just clock speed, like how fast do they move? And here the brain does not stand a chance. Like, so the clock speed of computers these days is measured in the gigahertz. That's billions of cycles. That's billions of cycles per second. The clock speed of the brain is about 10 per second. The reason for this is that when a synapse fires, sending a signal from one neuron to another, right? So you have a bunch of neurons in your brain, and each neuron is connected to about 500 to 1,000 other neurons by synapses that can send a signal from one neuron to another. When a synapse fires, it takes about 100 milliseconds to do the electrochemical reset before it can fire again. So lots of data from neuroscience about that, about 100 milliseconds. In fact, if you look at the rules in athletics, an athlete will be disqualified if the reaction time is less than 100 milliseconds. And you look at the times, if you download those apps to test your reaction time, you just cannot get it under 100 milliseconds because that's the clock speed of your brain. So in one case, billions per second, in the other 10 per second, we stand no chance there. But there's a lot more than just speed. What do? We make sense of an incredibly complex environment around us. And to make sense of a complex environment, you need a complex system. So let's look at the measure of complexity. Again, it's hard to compare, but let's look at the measure of complexity. And I think it's reasonably fair. Let's count the number of things that can be on or off. On the side of the chip, let's count the number of transistors, PNP junctions, things that can be on or off. On the side of the brain, let's count the number of synapses that may send a signal from one neuron to another or not. What do you think is more complex, a chip or the brain? Most people say, yes, the brain is far more complex. How much more complex? Millions of times more complex is most people's intuition. And that intuition would have been absolutely right not that long ago. Right now, here's what things look like. So the brain is about 100 billion neurons. Each of those has 500 to 1,000, let's say 1,000 synapses. So it means that we're looking at 100 trillion plus synapses, right? So that's roughly a sense of the magnitude of the complexity of your brain, 100 trillion. Transistor counts in chips right now are going over 100 billion. They're pushing into the 100 billion. So we're talking here about 1,000. That's very different from what things looked like just 10 years ago, right? Remember this scale, this logarithmic scale of growth in speed and complexity. Before we had a difference in system complexity between what the brain looks like and the kind of computational systems we can put together. The difference in complexity was in the millions, 6 orders of magnitude and more. We're down to 2 orders of magnitude. It's not that big anymore. So you start seeing computers do things that look and feel a lot more human because we're starting to approach the same level of complexity. In fact, if you look at the chip that I just showed you from Cerebral Systems, they're already at 2 trillion, right? So this is less than 2 orders of magnitude by now. What are we using? Okay, let's say 1,000 times more complex than any computer. What are we using that for? I mean, clearly it's not to go through databases or to solve spreadsheets. What do we use that incredible complexity for? Make sense of this. Let me bring an idea from psychology. Many of you may have read Danny Kahneman's book, Thinking Fast and Slow. And it talks about this idea in psychology of system 1 thinking and system 2 thinking. System 1 is the fast, the automatic, the intuition, the quick judgment. System 2 is the kind of thinking that you do when you are aware that you are thinking. When you can see yourself think, you are engaging in system 2 thinking. Let me clarify this for you with 2 simple questions. This is also from Danny's book. They seem silly, but they make the point. Ready? Here's the first question. What's the answer to this? Do you know? Of course you know. It's automatic. It's very easy. Second question. What's the answer to this? Do you know the answer to this? Well, right, what do you mean by know? You know how to follow a process that will get you at an answer. You take the 4, you multiply by 7, you get 28, you keep the 8, you carry the 2, multiply the 4 by 1, bring the 2, you get 6. Do the same thing with the 2, shift by 1 digit, add them all up and carry as needed. We all know how to do this, but it takes effort. You can observe yourself thinking in order to get at an answer. So this is system 2 thinking. How you got this answer just popped into your head. That was system 1 thinking. For the computer, they're exactly the same. It's 1 clock cycle, 1 arithmetic operation. They're exactly the same. What's happening in your brain is just fundamentally different. The amazing complexity in your brain is not about this. It's not about the 17 times 24. That insane complexity in your brain is about this. It's the things that just feel easy. It's not easy. The task that you engaged in here, recognizing these squiggles on the screen and making sense of all this information, knowing that 2 plus 2 is 4, it's an incredibly complex set of cognitive tasks, but it feels like a 0 effort task. The answer just pops. So that insane level of complexity in your brain is dedicated to make certain automatic, intuitive tasks feel easy. That's system 1 thinking. Another example is driving a car down the road, right? Once you've learned to drive and you've been driving for a few months, this feels easy. If you have to back up your car into a tight spot, even if you've been driving for years, feels a little bit stressful. Think about it from the point of view of getting a computer to do these tasks. Self-driving cars, we've been trying to do this for ages, and it's really, really hard. This example is from Waymo, so Google's venture into self-driving. You can see what they're trying to do. You know, that's a car, that's a bicycle, that's a sign. This is an incredibly difficult. It feels easy. It feels so, you know, look at this. Of course, that's a car. Of course, that's the road. Of course, that's the median. It's really, really hard to get a computer to do this reliably. Parking a car, backing a car into a tight spot. This is a system to task. Give the computer the rules of Euclidean geometry, give it the sensors to measure the geometry of the space, give it the rules of the geometry of the steering. It will calculate the trajectory, follow it exactly, and put it exactly right by the millimeter first time around. Very stressful to us, very easy to automate because it follows a very specific process which we can describe and have the computer follow. The intuitive sense making of a complex environment, that's insanely hard. We've spent now many billions of dollars trying to do this collectively as humanity. And most leaders of these businesses trying to do self-driving have come out and said, look, we cannot do this. I mean, technology is amazing. It has a lot of value. All these active safety systems are absolutely incredible. They're already being deployed in high-end cars and starting to trickle down. They can do things like, you know, a child jumps into the road ahead of you before your brain even knows that something happened. Remember the 100 milliseconds? Before your brain even knows that something happened, the car is already braking, right? So they'll do amazing things, but fully replacing a human. Imagine driving a car around the Place de l'Étoile in Paris or driving a car around a city like Jakarta. The environment is just so incredibly complex. The kind of sense making that you need to engage in until we have computers that catch up with the kind of complexity and sense making of the human brain, we just cannot do this. We can do on the freeway, controlled environments, predictable environments, lots of economic values, a lot of applications, but fully replacing a human, that's another story. So things that computers do well and don't, you know, the first task I have here is recognizing between Blue Mary muffins and Chihuahuas. It kind of throws you off, but computers do this very well because there's no sense making involved. Look, it's a one object recognition problem. Is it this or is it that? And I give it enough data to train it. It can recognize the texture and do a very, very good job. It just does not make mistakes. The second one, what is this? Well, it's obvious to me. It's obvious to you. Of course, it's an elephant. But most image recognition systems, you show them this image. Can you guess what they will say this is? They will say with 99% probability, this is the image of a cat, because this image has been artificially rendered with the shape of an elephant and the fur of a cat. And the image trained on a lot of data will pick up on the things that it finds reliably attached to a certain description of a cat, which is the fur. It recognizes and identifies a particular texture much better than we can and assigns a high probability of this being a cat, right? And then you can tweak the systems to avoid this kind of pitfalls. But then they are always very fragile. This ability to step back and make sense of things, the kind of task that you need to do the self-driving, it's just incredibly hard to automate, right? So that's that insane complexity that you have in your brain. So let's talk a little bit about the history of computation. And I want to use two examples to make again the point between system 1 and system 2 and the parallels in how we go about building computational systems. I'm going to use two examples. The first one is the chess match between Deep Blue, IBM's Deep Blue, and Garry Kasparov. There used to be this idea that chess was the ultimate test of human intelligence. The best chess player is the most intelligent person. This is actually not true at all. The measured correlation between general intelligence, IQ tests, and chess ability, the correlation is actually quite weak. It's a very narrow skill. It's an amazing skill, but it's a narrow one. There is a positive correlation, but it's weak. Up to the 90s, up to this point, the general belief was that a top human player would always beat a computer. There's just no way you can build a computer that will perform better than a human. And so when IBM challenged Garry Kasparov to this series of games, that was the expectation, that Kasparov would carry the day. And as you might remember or know, Deep Blue won, right? To everyone's great shock. This is my question. If you were to ask in 97 to the IBM engineers, in game 3, move 27, why did Deep Blue play knight to f3? The IBM engineers would be able to answer that question very precisely, because Deep Blue was playing with tree search. Right? For those who don't know what tree search here is an example of using tic-tac-toe. You know, the game of crosses and circles. In the first move, you can play in the center, in the edge, or in a corner. And then you look, okay, if I play in the center, my opponent might play on an edge or on a corner. And then where can I play? You can go on and build the whole tree. And then you look at the bottom of the tree, you look at the leaves and you see who won. And then you back propagate through the tree at each level, choosing the best path depending on whose turn it is to play. And then you see who wins in which branch of the tree. And based on that, you play the best move. So this is tree search. So to say, well, he played the knight to f3 because if he didn't, then Kasparov could do that. And by playing this, then the moves that are available to him look like this. And this is what I would do. So you can look, you can inspect the tree and answer very precisely why did it play this move. A lot of people then turn to the game of Go. The reason was we just could not build computers to play Go. I mean, you could build them, but they would play ridiculously bad. The reason for that is that it's a game that has a lot of moves and a lot of branching in each node of the tree. That is, the tree is horrendous from a computational point of view. There are 19 by 19 places where you can place either a white or black piece, depending on whose turn it is. So let's call it roughly 400. So right on the first move, there are 400 branches. And in each of those, your opponent can then play in almost 400 different places. So every time you go down one layer of the tree, you multiply everything by 400, and then you cannot just search 5 or 6 or 7 moves as you would in chess. Look, there's 300 moves in a game. To make sense of anything that might happen, you need to search dozens of moves down the tree. So having to search dozens of moves down the tree with each move branching by 400, it's insane. You just cannot. Computationally, it's infeasible. You can do the numbers, you just cannot. You just do not have, and you will never have the kind of computational power. Right? So the universe is not long enough to search this tree, no matter how much computational power you have. So in 2016, DeepMind, so Google had acquired this British company called DeepMind, and they challenged Lee Sedol, the top human Go player, to a series of games. And again, everyone expected Lee Sedol to play, right? Humans don't play by tree search. They don't play Go by tree search. For chess, it's a mixture. Players do a bit of tree search, but a lot of it is intuition. They play a lot by intuition, right? So they can say, you know, this position looks good, this position looks bad, right? So there's a measure of intuition and there's a measure of tree search. In Go, there's a lot more intuition, right? There's certain names that people use for different configurations of the board that they're trying to get at. So it's a very intuitive kind of play. Again, everyone expected Lee Sedol to win. If you remember what happened, it was a washout. I mean, AlphaGo completely destroyed Lee Sedol. This was very surprising to a lot of people. And here, let's return to the same question. If you were to ask the Google DeepMind engineers, why did AlphaGo play, move 17 in game 4? Why did it play that move? Do you know what they would say? They would say, we have no idea. We have no idea. There was an element of tree search in the algorithm with stochastic tree search, but at the core of it was a reinforcement learning engine that learned by playing, a very complex nonlinear function that kind of mimics the structure of the brain. You have these nodes, you know, they developed specific hardware, these tensor computing nodes that kind of mimic the structure of how the brain functions, in where these nodes and have these weights that carry the signal from one node to the next. And then what you do is say, well, this allows you a very large range of very complicated nonlinear functions. Which one do you choose? Well, let's train it on data. Let's apply this nonlinear function on the data. If it gives a good answer, do more of that. If it gives a bad answer, do less of that. And you do this over and over again. If you're doing image recognition, you would train it on labeled data. In the case of Go, you train it on games. You make it play against itself. When it wins, that was good, do more of that. When it loses, that was bad, do less of that. And you keep adjusting this nonlinear function to teach it to recognize what is a good position and what is a bad position. So if you were to ask the DeepMind engineers, why did AlphaGo play this move? They would say, well, it's based on a very complicated nonlinear model, which was developed very slowly by learning from examples. These models consume a lot of energy and a lot of computational power to be trained. But once the model has been trained, then we have the function, training the function and adjusting the weights until the function gives you good answers is incredibly expensive and incredibly time-consuming. But once you have the function, you can calculate it very quickly. You can apply it very quickly. Training a large language model is incredibly expensive. Once you have it, you can run it very quickly. This looks a lot like human intuition. We have this very complicated brain that allows us to generate these intuitive responses to our environment. How do we develop? It takes years. When a baby is born, the baby is completely clueless, and it takes years and years of experience and education. If you do things wrong, if you don't do this well, you will produce a very unhappy and unproductive human being, right? So it's training human intuition and human judgment is also very expensive. But once we have it, yeah, 2 + 2 is 4. I just know that. It's very cheap. It comes out very quickly because, again, it is this very complex nonlinear function, which is my intuition, that has been trained on years and years of experience, but then allows me to do things and to recognize, oh, that's a bicycle on the road, 2 + 2 is 4, allows me to have these intuitive responses very effectively. In a professional environment, this is a safe investment, this is a risky investment, this project is on track, this technology is likely to run into problems versus not run into problems. How do we make these judgments based on intuition that we develop from experience? If you look at the commentary from chess grandmasters around, because then they turned the machine and built a chess version of it based on reinforcement learning, and had it play against the top software that existed at the time, which was Stockfish, which was a tree search algorithm. It played much better than any human, but Stockfish played a kind of chess that people describe as sort of like ugly engine chess. It played this chess which would beat a human, but was very unelegant. It was based on searching the tree deeper than you and finding these quirks, these weird quirks on the search tree. That means that this position, even though it doesn't look good, it leads to a win. But AlphaZero played a very different kind of chess. You look at it and it's bizarre. It feels very human. It's very tactical. It's very intuitive, just much better than any human player, right? At this point, it plays at an ELO rating of 4,000, which is just at an incredibly superhuman level. But it feels very human, just more so, because it's playing not just by tree search, it's playing by training this intuitive response, this intuitive reading of what is a good position strategically, and then playing towards strategically good positions, right? What a top grandmaster will do. Of course, Google didn't acquire DeepMind to play chess and to play Go. They acquired DeepMind because they wanted to deploy that stuff in their operations. And the first deployment that they did was on Google Translate. If you remember what Google Translate and every translation system looked like before 2016, systems up to then were very much system to kind of computation. Let's take our knowledge of linguistics. Language is composed of sentences. A sentence has a subject and the verb, there are adjectives, blah, 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 right? So describe the structure of sentences. And then you have a table. Here are words in English, and here are words in French, and here are words in Chinese Mandarin, and here's the table that maps them, right? Now take the sentence in English, break down the components, go to the table to find the equivalent, to rebuild it in the other language, and that's how you did translation. The results were just laughably bad. It's just laughably bad. Then in 2016, they did this with announcement. But at one point, there was one day, I remember the day specifically, I went and used Google Translate, which was embedded into the Airbnb comments translation system. And suddenly it was bizarre. It just looked so good. It used to be laughably bad. And suddenly it was just shockingly good. What happened on that day? Well, they flipped the switch. It went from a system to kind of computation based on our knowledge of linguistics and dictionaries and so on. It went from that to a system that was based on the DeepMind technology that had been trained on data. This non-linear function mapping one language to the other that was trained on a set of data, meaning texts that have been translated by humans. So before, if you ask why did the system do this translation, you could audit it. Right now you can't. Well, I don't know. It's why did it translate this that way? I don't know. This neural network was trained on data and decided that this was a good translation. The latest large language models, that is training these neural networks on data, GPT-4 is now one. They don't disclose. You know, there's an irony in the name OpenAI. They're not open at all these days. But from the rumors, it's around 1.7 trillion parameters, right? So that's just 2 orders of magnitude off from the complexity of your brain. So that's where we are. That's the progression of large language model, reaching a level of complexity. Yeah, we're training these non-linear functions that kind of mimic human intuition, that are starting to approach the level of complexity of our brain. The amount of resources that's going on right now to training these systems is just mind-boggling, right? So last quarter's revenues from NVIDIA is $10 billion, just revenue specifically from the data centers that are being used to train AI models, which means that probably around $100 billion are being spent every year right now to train these models. And the share of NVIDIA, to everyone's surprise, when NVIDIA was this specialized maker of graphics cards that had a valuation that was a fraction of Intel, now it has a valuation which is 10 times that of Intel. Why? Because their graphics cards have now been repurposed and they've designed, of course, now GPUs specifically for running these models. So let me skip this. Let me go here. So here's an example. So I asked 2 of my kids to give me a prompt for Midjourney. One, the oldest girl, said a flamingo crocheting, a peaceful ocean in the background. The boy said, my second child said, an octopus mathematician. And this is what came from Midjourney. So first couple of comments. One, like it's amazing, right? As we know, the results are quite amazing. One thing you can see is that there's some shortcomings in the sense making, right? It's not the flamingo that is crocheting. The flamingo is made of crochet. It's not an octopus mathematician. It's an octopus with a mathematical structure. The other point that I want to make with this example is that the system gives you 4 options, and each of them represents a resetting of the network and regeneration of the image. All of them look really good, but they are very different from each other. This is a fundamental feature of this kind of intuitive systems. These are very nonlinear functions that have many solutions, many answers that are reasonable, but they are very different from each other. this is not just an issue with neural networks. That's an issue with this mode of computation, a non-linear function that gives you a quick intuitive answer about a question, whether it's your system one thinking in your brain or whether it's a neural network that you trained. It has this fundamental feature. It's a very high dimensional non-linear function that will have many local optima. In our brain, we cannot do the reset and look at the problem again. We tend to look at the problem, come to a conclusion, and become anchored, fixated on it. We don't have this privilege that the computer has of just resetting and running again. So there's something to be said here about the things that it might be very useful for us to allow us to get fresh intuitive takes on the same problem. Of course, if you look at DALL-E, the latest version of DALL-E, you can see that it's gotten much better. Like now it's really an octopus mathematician. Now the flamingo is crocheting, although there's something weird. If you look at the arms of the flamingo, they still seem to have arms made of crochet, right? So improving a little bit of the sense making, but this is something that it fundamentally struggles with. If you look at ChatGPT, I gave it this question. Use the numbers 25, 2, 10, 8, 7, and 4 to make an equation that results in 739. Use only the basic operations and each number once, as per the rules of the show Countdown. This is a British quiz show. And it responds with great certainty. Certainly, here's one way you can arrange the numbers to make an equation that results in 739. Can you spot the problem here? Yeah, it doesn't add up to 739. It adds up to 411, right? And everyone has seen examples and versions of this. Because what is ChatGPT doing? It's a nonlinear function trained in the corpus of human text that produces things that look like that. So it's a little bit, you know, what we call a bullshit artist, you know, people who are really good at saying stuff that sounds good, but then you think about it, doesn't really make sense. There's no sense making underneath. You know, the synergy of joint ventures in China with the leverage, like people are very good at talking like this, but then you dig into it, there's no underlying sense. Well, ChatGPT is just the world's greatest bullshit artist, right? It's just exceptionally good at that, right? But of course, sometimes there's lots of uses for that if you can harness it correctly. In this case, I told you, well, the question is wrong. And it says, you know, it becomes humble, but again, let me correct that. It gives me an answer that's even worse. And say, that's wrong again. Gives me another one that's even worse. Of course, this was ChatGPT 3.5. If you go to ChatGPT 4, so it went one order of magnitude up. So ChatGPT was on the order of 100 billion parameters, and ChatGPT 4 is on the order of 1 trillion parameters. I give it the same question. It gives me a very interesting answer. It says, it appears that there isn't a straightforward solution using basic operations. It may require a different set of operations or a different approach. If you have specific constraints, or if you have additional operations in mind, please let me know. But just addition, subtraction, multiplication, division, it's not possible. It's telling me about impossibility, right? So very interesting. There's only a problem with that, is that it took me about 30 seconds to find a solution, right? So it's saying, oh, I cannot find it, therefore nobody can. Right? Which again feels very human, right? Feels incredibly human. It's overconfidence. Oh, I could not do it, nobody can. It's not a surprise that it does behaviors that look a little bit like things that humans do when they're relying on pure, just intuitive generation without reflection, because that's exactly what the systems are. Just very fast, human-like intuitive generation, the kind of thoughts that you have when you wake up in the morning and you just woke up from a dream and you are very confused and just ideas come free-flowing without any guidance of reasoning. That's exactly the kind of output that you can expect from the systems, because that's the kind of computation we are doing. If you ask what this is ChatGPT's representation of what a bullshit artist looks like, right? But sometimes it's very useful to have a bullshit artist on your side if you can harness it correctly. So we're a bit late, so let me skip this one. Yeah, this is another one. This was from, just to show, yeah, it has solved some. I gave you the example of the flamingo and the octopus. But again, these are sort of it's not particularly deep sense making. You can still have it learn that kind of sense making from data. But when it requires a more deep and more reasoned sense making, it still struggles. This is from an article in IEEE Spectrum, an example of an image generated with a prompt, an illustration of the solar system drawn to scale. This is what it gave it. Right now, I just did this a couple of years ago with Dolly, with ChatGPT. So the latest version, it's still giving you a completely nonsensical answer. It's gorgeous, it looks beautiful, but it doesn't make any sense for the prompt that I gave it. So the sense making, the connection between intuition and reason is just not there. So this is our traditional picture of human cognition. There's system one, the intuition, the ideation, pattern recognition. And there's system two, the kind of thinking that you do when you can observe yourself think, when you are following a sequence of reasoned steps and you are aware and you are actively guiding that reasoning, that's system two. But there's much more to it than just system one and system two. For this stuff to work, the two have to talk to each other. It's a very complicated interaction between the two that builds our cognitive abilities. System one guides reasoning and system two guides intuition. We need reasoning to direct our intuition, and you need the intuition to direct the reasoning. That's what makes our humanity in terms of our ability to make sense of the world with this mix of reasoning and intuition. What have we done with our development of computational systems? First, we developed a version we automated system two. We built tools. I don't have to learn addition and multiplication. I can use a calculator. I can use databases. I can use spreadsheets. Even for symbolic computation, I can use symbolic computation tools like Mathematica to do what I could do in terms of following a sequence, a well-defined sequence of steps, and do it much faster than a human can do. What is new now is that we also have tools to replicate what human intuition does. It's machine learning methods, large language models, generative AI. They can do what our intuition does at an incredibly sophisticated level. But this piece, the connection between the two, is entirely missing. That's the current frontier. Until we can do this, there's some first steps that have come, but still in very specific problems, tying symbolic computation to reinforcement, to neural network methods, and making them work with each other with some very interesting results, but it's really, really early stage. Now, we honestly do not understand this very well. So this is a sequence of evolution. So system two, we've been able to do this since the 1950s, faster and faster, and amazing things with it, enormous contributions to humanity. What is new from the past 5-10 years is that we can now replicate system one thinking, just intuitive responses at a human, even superhuman level. And we can use it as tools. But the connection between the two, that's where humans are fundamentally for and will be for a very long time. This is the cutting edge of research. It's not clear how long it's going to take, probably quite a while. And so when you think of replacing humans, you just cannot. You can use these tools to supplement intuition, to supplement computation, procedural computation, but the interaction between the two, you need a human for that. The next step, the things that motivate us, do you need emotions for these systems? We know that in humans, you need emotions for reason to work. Reason does not work when a human has the emotional center of the brain damaged. The reasoning stops working. So we know that in humans, we need a functioning emotional system for the reasoning part of the brain to work. Will this be the case in the computers? We just don't understand this at all. So that's what I want to leave you. So at this point, these things, it's incredibly fascinating, but we're very, very far away from general intelligence. So think of it as tools. We have tools for procedural computation. You can do system two kind of calculations much faster. We've been able to do that for a long time. What is new is that you have tools to likewise have superhuman intuition. But what a human does is far more than that. It's the linkage between the two systems. We cannot do that yet. So let me stop here because I'm getting nudged by our kind hosts about leaving time for questions. So let me pause here to let Savita step in.
Perfect. Thank you so much, Miguel, for the insightful talk. I am a hardware design engineer, and we took great pride in increasing the number of transistors we taped out each year. And the complexity is only going to explode to get AI where it needs to be. It's very, very exciting times in the compute world indeed. So we have a lot of questions coming up, and I think it's going to move quickly. So I'm going to try and summarize questions that are similar in nature. And I'm going to start off with a lighthearted question. If you've already managed to automate intuitive decisions with computers, how far do you think we are from automating wise decisions?
Very far, very far. Because as I said, sort of wisdom is at the intersection between reasoning and intuition, right? So reasoning allows you to follow a sequence of steps to get to a conclusion, but that's very limited in its ability to handle very large, as we saw. You cannot play the game of Go because it's too complex. When a situation is too complex, you need to rely on an intuitive response. But if you rely on a purely intuitive response, you get the kind of nonsense that I showed you. I picked that example. Everyone has seen examples of this, where ChatGPT gives you nonsensical answers because it's just giving you something that sounds good, untethered from reasoning. So wisdom is really at the intersection of the two, right? And I think what's beautiful right now is that we are kind of maybe things will change eventually once computers can also do this interaction between the two, and then we're going to have to think about complicated issues of governance, but that's probably 10, 20 years down the road. So right now, the beauty of it is that you can think of these tools being able to do very fast procedural computation and being able to do very fast and also to repeat intuition, right? Your brain has one intuition and then it becomes fixated on that. You look at a, I don't know, marketing problem or a strategy problem or a technology problem, we come up with an answer and we believe, oh, this must be the truth. With now we can use the computer's intuition and just reset several times and get and see a range of options and avoid these anchoring effects that the brain is prone to, right? So we can now use superhuman computation, superhuman intuition, and just harness the two of them, right? And that's where wisdom lies, is really at letting reason guide intuition and letting intuition guide reason.
Perfect. Yeah. So I'm going to move on to a question that involves a little bit of advice. So if can system 2 thinking migrate to system 1 thinking? How can we as humans migrate our thinking to be able to effectively use Gen AI type tools? Most of us don't. So is there going to be a difference between using ChatGPT and a junior analyst, if that makes sense?
Yeah, I mean, the junior analyst will still be able to do things that ChatGPT cannot when it requires a complex judgment between, there's two things. One, complex interaction between reasoning and sense making and intuition and processing loads of information. You still need a human for that. Plus, by making the junior analyst do that, you are training a human to have the experience to then, become senior and partner and so on, right? If they need to start somewhere and build that experience. It's not really a migration. I mean, and it's really about, well, the tools are still going to evolve, right? So like, look, there was a point where the evolution in databases, in spreadsheet software was just incredibly fast. And every year, was Lotus 1 to 3, and then it was and then Excel came up, right? It was changing very fast. And you would learn a tool, and then suddenly that tool would disappear from the market because the other one was better. And it was kind of frustrating. Like, we kind of, at that point now with the system 1 tools, right? With the system 2 tools, databases, spreadsheets, and so on, it's very mature. It's very stable. We have learned to use them, and every analyst uses them in their job and knows how to use them. System 1 is in that phase, remember the late 80s, actually many of you don't remember, but I do, where things were changing very fast, and it's kind of frustrating because you kind of start learning a tool and then there's a better one or there's a different one. We're still there, but I think we'll come to a point where we will learn to use these tools the same way we learned Excel. It's just that they're not mature yet, they're not stable yet, they're still fast improvements and iterations, but my best guess, and again, who knows? It's my best guess is that it will evolve to become tools that we learn to use to supplement our intuition, to give us superhuman intuition in the same way that you can think of as Excel. Excel gives you superhuman powers at doing calculations, right? You know, it's not that long ago that people did the kind, what you take now for granted in Excel, go back a generation or two. This was brutal work that everyone spent, you know, a ton of time doing all these calculations by hand. Right now, we take it for granted; it does it for us, right? So we're going. So that's replaced a lot of system to work by humans, and we're going to replace a lot of system one. It's going to give us superhuman abilities, but we're going to remain for a long time as the driver who uses these two engines to come to, was said, as was articulated in the previous question, to wise results, to wise answers, wise decisions.
Yeah, I think that gives a lot of comfort to people like in an MBA cohort who are wondering what we are going to do if ChatGPT is going to do everything. So yeah, definitely. I think going hand in hand with what we still stand for, our intuition, and then using these tools to complement that is going to be the way forward for many, many years. So moving on to the next question. So to your point of ChatGPT being a bullshit artist, even with the evolution into 4, as it keeps searching the World Wide Web for answers to queries, isn't there a risk that the www will become too polluted and you'll have more unreliable?
It's not a risk, it's happening already. It's not a risk, it's happening already. And you already start seeing examples of results of the bullshit that is especially bad because the first generation tools were even worse. ChatGPT 4 is significantly better, but the first generation tools that were widely available and free were much worse, and they were used a lot by people who were spamming and generating content in all sorts of ways, which now has been read by the latest generation tool. And you can find examples already of nonsense appearing, so like what they call hallucinations, which basically is bullshit, right? Appearing as in the answers of systems that are not prone to that. They're not hallucinating, they're not giving you bullshit, they're just giving you the bullshit that they learned from the previous generation of bullshit content that was put on the web. Yeah, that's a huge issue for sure. That's an enormous issue. And eventually we need to get to the point where we have, again, it's the connection to sense making, right? So this problem will get worse until we have an ability to connect the systems in a more meaningful way to sense making.
So next one is an interesting one. Do you see the human brain evolving as AI develops, because we no longer will use the same functions as we did before?
I mean, human brain is the result of many millions of years of evolution, and it's not going to change easily. I mean, we do have evidence that things have changed in humanity over the years, but mostly as a result of nutrition, education, and so on. I mean, I think it's just the skills we train people for and that people develop will definitely be different, right? So before the 1980s, the ability to do a lot of calculations in your head and to do a lot of calculations on paper very efficiently was at a very high premium. People got paid. If you look at the old movies about NASA, you know, there were like these rooms full of people during the Second World War. There were, you know that a computer used to be a job, a human job. This was a person who did computations, right? That's why computers got called computers, because this was a human job doing calculations, right? And that disappeared. Like, sure, it's still useful to have a sense of order of magnitude, to be able to do calculations, to understand the order of magnitude of things. That's incredibly important. But the ability to do square roots exactly to the 4 decimal places quickly, who cares, right? So I think a similar thing is going to happen with certain intuitive tasks that we thought of being quintessentially human. You know, they're not. They're going to become just a tool that we use, right? Of course, in a way you could say, well, I am much better at computing square roots than someone back in the 60s was, because I can fire up my phone and open the calculator and do it more quickly, right? So I think a similar thing is going to happen with a lot of tasks that we thought, oh, only a human can ever do this, right? But the problem is the same way that until we have computers doing sense making, and that's a completely different story. 20 years from now, the conversation might be very different, right? But right now, in the same way that, okay, you can automate calculations, but you cannot make the calculations make any sense. You need an engineer that understands the problem. You need an accountant that understands the problem. You need someone in finance that understands the market for over-the-counter derivatives and the risk. You need someone who can make sense of the numbers for the numbers to be useful. The intuition is going to be the same thing. You can have a tool generate images, but you need a professional designer to make sense of what is a good image and the aesthetic and how it fits with this segment of customers and how it fits with the history of blah, blah, blah. So you still need humans, just those humans will have much more powerful tools and be a lot more productive.
Perfect. So I think we have time for one more question, and then the rest, I will summarize them and send them to you. Maybe we can send it out as a summary later. But the last question before we wrap up is there an independent review and evaluation of AI systems, something similar to the Gartner quadrant? Decision makers would definitely welcome this help in this field to make informed and objective decisions.
So I'm not sure I understand the question in the sense, independent review in terms of someone assessing the quality of the system, talking in terms of safety or in terms of quality?
I would assume in terms of safety.
Yeah, so both of those are very relevant questions. And right now it's a little bit the Wild West. And we need to be thinking about those things very fast and very hard. At this point, the risk, I mean, all the stuff about existential risk, I mean, sure, it's an issue that we will have to think about maybe 10, 20 years down the road. It's not an issue now. Right now, it's a distraction. There are serious harms that are happening right now and serious risks that are present right now that are completely different. It's not about the thing taking over from humans. It's about the power that it gives to bad intentioned actors to cause damage, right? To flood the information space with disinformation, to run harassment campaigns, all sorts of things like that, right? It gives very powerful tools for people to distort reality and manipulate others. So the risk is not the AI per se, is the harms that a human can do with that tool, right? That's the things that we need to be thinking about right now. The existential risk stuff eventually down the road. In terms of assessing quality, yeah, I mean, people are now, I mean, Microsoft and Google, to their credit, have been actually more open than OpenAI at sort of disclosing their research and audits on their models. And we need a lot more of that, right? We need to maintain that culture. There's a reason because suddenly there's kind of a gold rush. And so companies that used to have a culture that came very much from academia and from computer science of very open and peer review and sharing of information. And suddenly there's a gold rush. And so people are closing a little bit, right? Then things will become potentially a little bit more complicated to manage, both in terms of audit for quality and control for risks. Yeah, but that's a whole very long conversation, right? There's different regulatory approaches being pursued in the US and Europe. I think there's virtues to both. The US system relies more on the legal system and liability. Like the system is not liable. The human who runs the system is liable, and if the system does bad thing, you as a person who are responsible for the system will be liable. You cannot say, "Oh, I was not racist, the system was." No, you put together the system, you are personally liable. That's roughly the US approach. The European approach has been a little bit more explicit in its regulatory approach, obligations of transparency and control and auditing. I think both have virtues. Eventually it's actually nice that people are taking different approaches in different places because we can learn and then see what works. But yeah, we'll definitely need a lot more of that.
Perfect. Thank you so much, Professor Lobo. I'm going to make sure I have all the remaining questions summarized, and I'm going to hand it back to you at this point to wrap us up, and we can drop off.
Thank you, Savita. Thank you, everyone.